Guidance for inspectors on-stream and off-stream inspection of FinFan coolers, air-cooled heat exchangers, best practices for thorough inspection of cooling equipment. Purpose, scope, and applicable standards. This section establishes the engineering intent and regulatory basis for inspecting FinFan coolers, also known as air-cooled heat exchangers, AHEC. The primary purpose of the guidance is to support inspectors in performing consistent, code-compliant on-stream and off-stream inspections that ensure mechanical integrity, operational reliability, and personnel safety. FinFan coolers are widely used in refineries, petrochemical plants, and gas processing facilities, where they often handle high-pressure and high-temperature hydrocarbons. Failures can result in leaks, fires, environmental releases, or extended unit downtime. Therefore, inspections must be systematic, risk-informed, and aligned with recognized industry standards. The scope of inspection includes pressure-containing components such as headers, plugs, nozzles, and associated piping, as well as non-pressure components that affect integrity and performance, including tubes, fins, fans, motors, gearboxes, and structural supports. API 570 governs in-service inspection of piping systems connected to FinFan coolers and establishes requirements for thickness measurement, inspection intervals, corrosion rate determination, and remaining life calculations. API 572 provides detailed guidance on damage mechanisms, inspection methods, and inspection planning principles that are directly applicable to headers and tube bundles. Even though FinFan coolers are not traditional pressure vessels, ASME Section 8 and ASME B31 codes define original design rules, allowable stresses, minimum required thickness, and repair acceptance criteria. Inspectors must understand how these codes interact. API 570 typically applies once the equipment is in service, while ASME codes define the design basis against which in-service condition is evaluated. This section emphasizes that inspection decisions should be technically justified, clearly documented, and traceable to code requirements. It also highlights the importance of using OEM documentation and site-specific procedures to supplement code guidance, particularly for mechanical components such as fans and drive systems. Air Cooler Heat Exchangers, AHEC, Design Overview and Critical Components. FinFan coolers operate by transferring heat from a process fluid flowing inside tubes to ambient air that is forced or induced across external fins. Understanding this design is essential for effective inspection because damage mechanisms and inspection focus areas are directly influenced by operating principles. The tube bundle is the primary heat transfer element, typically constructed of carbon steel, low-alloy steel, or stainless steel, with aluminum or carbon steel fins mechanically bonded to the tubes. Headers distribute process fluid into and out of the tube bundle and are considered part of the pressure boundary. These headers are often the most critical inspection locations due to complex flow patterns. Erosion, corrosion, and local turbulence, fans, motors, gearboxes, belts, and fan blades are mechanical components that do not contain pressure but are essential for maintaining adequate airflow and heat transfer efficiency. Structural elements such as frames, supports, and access platforms must withstand vibration, wind loading, and thermal expansion. From an inspection standpoint, inspectors must differentiate between pressure components governed by API 570 and ASME code acceptance criteria, and mechanical or structural components that are assessed based on fitness for service, OEM limits, and good engineering practice. Common damage mechanisms include internal corrosion from process fluids, erosion at high-velocity inlet zones, underdeposit corrosion due to fouling, and flow-accelerated corrosion in certain services. Externally, atmospheric corrosion, fin degradation, mechanical damage, and vibration-induced fatigue are frequently observed. API 572 provides valuable guidance on recognizing these mechanisms and selecting appropriate inspection techniques. By understanding the design intent and operational stresses of each component, inspectors can prioritize inspection locations, select effective NDT methods, and make sound integrity assessments. Objectives, safety, and on-stream inspection activities. On-stream inspection refers to inspection activities performed while the FinFan cooler remains in operation. The primary objective is early detection of deterioration without interrupting production. On-stream inspections are inherently limited in scope but are critical for identifying developing issues such as leaks, abnormal vibration, corrosion progression, and mechanical damage. Safety is the foremost consideration during on-stream inspection due to rotating equipment, elevated temperatures, noise, and work at height. Inspectors must comply with site permit-to-work systems, maintain safe distances from fans, and use appropriate personal protective equipment. Visual inspection is the most common on-stream technique and includes checking for evidence of leakage at header plugs, nozzles, and flanges, observing fin condition and cleanliness, and assessing structural supports and fan guards. API 570 allows and encourages on-stream thickness monitoring using ultrasonic testing on accessible piping, headers, and nozzles. These measurements are used to establish corrosion rates and remaining life calculations, forming the basis for inspection interval determination. Inspectors should select consistent measurement locations to ensure meaningful trending over time. Operational indicators also provide valuable inspection information. Changes in temperature approach, reduced heat transfer efficiency, or increased pressure drop across the exchanger may indicate fouling, tube blockage, or internal damage. Vibration and abnormal noise from fans or gearboxes may signal mechanical deterioration that could eventually affect tube integrity. Proper documentation of findings, including photographs, measurement data, and clear recommendations, is essential. On-stream inspection results often trigger more detailed off-stream inspections during planned shutdowns, making this activity a key element of an effective mechanical integrity program. Shutdown inspection, NDT, and internal examination. Off-stream inspection is conducted when the fin-fan cooler is shut down, isolated, and made safe for intrusive examination. These inspections typically occur during turnarounds or when on-stream findings indicate potential integrity concerns. Proper preparation is essential and includes positive isolation, draining, venting, cleaning, and compliance with confined space entry requirements. Off-stream inspection allows full access to components that cannot be adequately examined during operation. External off-stream inspection includes detailed visual examination of fins, tubes, headers, and structural components. Corrosion mapping using ultrasonic testing can be performed on headers and piping to identify localized thinning. Internal inspection of headers, guided by API 572, focuses on corrosion, erosion, pitting, underdeposit attack, and flow distribution issues. Tube-to-tube sheet joints are critical locations where leakage or cracking may develop. Non-destructive examination techniques are selected based on anticipated damage mechanisms. Ultrasonic testing is widely used for thickness measurement, while radiography may be applied to assess internal header conditions or weld quality. Eddy current testing is commonly used for tube inspection to detect internal corrosion, cracking, or wall loss. Results must be evaluated against ASME design requirements and API 570 acceptance criteria. Off-stream inspections provide the most reliable data for remaining life assessments and repair decisions, making them a cornerstone of long-term equipment reliability. Assessment of findings and code-based decisions. After inspection data is collected, inspectors must evaluate findings in accordance with applicable codes and sound engineering judgment. Thickness measurements are compared against minimum required thickness calculated per ASME design rules and API 570 requirements. Corrosion rates are calculated using historical data, allowing estimation of remaining life and determination of appropriate inspection intervals. When damage exceeds acceptable limits, repair or replacement options must be evaluated. Typical repairs for fin-fan coolers include tube plugging, tube replacement, header weld repairs, and localized reinforcement. All repairs must comply with the original construction code or an approved alternative and be properly documented. In some cases, a fitness for service assessment may be required to justify continued operation with known damage, provided safety margins are maintained. Although API 579 is not always mandatory, its principles are often applied to support engineering decisions. Risk-based inspection concepts can also be applied to fin-fan coolers by considering probability of failure and consequence of failure. Equipment handling flammable or toxic services may warrant shorter inspection intervals or more extensive NDT. This section reinforces that evaluation is not merely a calculation exercise but an integrated engineering process that balances code compliance, operational needs, and risk management. Inspection best practices and professional reporting. Effective inspection of FinFan coolers depends on consistent application of best practices and professional judgment. Early detection of corrosion, fouling, and vibration issues significantly reduces the likelihood of unplanned failures. Regular on-stream monitoring, combined with thorough off-stream inspections, provides a balanced approach to integrity management. Inspectors should work closely with operations and maintenance personnel to ensure observations are properly understood and acted upon. Competency is a critical factor. Inspectors must have working knowledge of API 570 and API 572, understand heat exchanger design principles, and be familiar with common NDT techniques. Field experience is essential for recognizing abnormal conditions and differentiating between cosmetic and integrity-related damage. Inspection reports must be clear, accurate, and traceable, providing location-specific findings, code-based acceptance decisions, and prioritized recommendations. Well-prepared inspection reports serve as engineering records that support maintenance planning, risk assessments, and regulatory compliance. By applying the guidance in this presentation, inspectors contribute directly to safe operation, environmental protection, and long-term asset reliability. The ultimate goal is not simply to find defects, but to manage degradation in a controlled, technically sound manner that aligns with industry standards and best engineering practice.